CTO and co-founder of BG Networks. It's my pleasure to be here today talking to you about rapid security hardening for embedded processors. We'll spend some time talking around the many technical details. We're going to use a particular processor as an example, and then we'll highlight our security automation tool that we offer to facilitate hardening embedded devices and do so very efficiently as well. So with that said, I'd like to provide a little bit of context of why security is important and why the need to implement security efficiently a design is important. And I think many of you may have already seen that security is becoming a top concern. It's given that you're joining us here today. I'm guessing it's definitely one of your concerns, but as we can see over the past several years, this is an increasingly a critical component of IoT and embedded designs. A survey done by the Eclipse Foundation, they do a yearly IoT and Edge Developer Survey. In the 2021, the survey that they did there, I have one person saying that they can't hear audio. I'll just pause here for a minute. Are others able to hear audio before we keep going? I'll try cycling. Okay, I see that others have responded that they can hear audio. So if you're not able to hear it, I tried cycling my audio. Hopefully the rest of you can hear me. I'm going to go ahead and keep going. Hopefully it's just a glitch and you'll be able to hear it momentarily. So the survey that we're looking at here in 2021, there's sort of two interesting things about the results there. One was that you have not only is security the top concern, but there's a pretty significant increase in the percentage of developers who have identified security as being that top concern. So from 39% to 46% identifying security as their number one priority. Security means a lot of things, though. So one of the things that we can also look at is other surveys identifying what have other developers been implementing in their designs. This is also a survey that was done by EE Times. It's a little older, it's from 2019. But if you look at this survey, you'll notice that these are the measures that were being performed and implemented in the design. The top 5 of those are encryption, authentication, secure boot, secure over-the-air updates, all kind of critical aspects of security. And then we'll start to see some more advanced capabilities such as intrusion protection as being a key element of that. When we're looking at that, if we look at secure boot, we're going to spend a good portion of this talk today discussing secure boot, what goes into secure boot. Part of secure boot does involve authentication and encryption. So when you look at in 2019, about 27% of developers were implementing secure boot within their system, but you can see more were using encryption and authentication. So of course, encryption and authentication have uses beyond secure boot, but they're also critical aspects of the secure boot process. We'll provide some more details there. The challenge that you face with implementing security is it does take development effort. And we all know that design cycles for products they get shorter and shorter every iteration. And you can see the majority of designs for Edge and IoT developers, the timeline for that development, almost half of them are less than 1 year in terms of that total development. So that gives us the challenge of we need to add security to our design, and we need to add it efficiently because obviously we don't want to extend our design cycles. And this is where we think automation can help harden security of your embedded IoT design without delaying the development times. So we'll talk more about what all goes into that today and how automation can help with that. But why is it so important here? I want to spend a little bit of time highlighting two key factors that are driving the need for security, because I think the context is very important. And I would obviously advocate that every design that's being produced should have security, and that's really twofold reasons that are driving this. One of them is the more devices you have, the more attacks there are. So the number of attacks on IoT systems are growing incredibly fast. We can see there's obviously each industry seems to have a highlight example that is maybe driving some of the changes that are there. In the automotive industry, there's obviously the famous Jeep hack by Miller Balasek that demonstrated the remote capabilities of getting access to control the brakes, the steering, and the engines. This was sort of an effort that started to lead to identifying the need for adding security to these designs. Other automotive manufacturers have, kind of in response to these earlier examples, have started to do robust penetration testing of their systems. So Mercedes-Benz, they worked with a company called Skygo to hand them a vehicle and say, can you get access to this vehicle? And they were able to get remote access to the door locks. They're able to get access to the engine start-stop capability. They were able to extract the firmware off of the ECU itself. And with that firmware, scan it to identify the software that was in there, and then cross-reference that with known vulnerabilities and found 19 additional vulnerabilities in that software. So security is very important. You can see similar attacks on printers, VoIP phones. There's the Colonial Pipeline attack that we saw a few years ago that essentially caused the pipeline to shut down. So there's a lot of these attacks that are happening with these systems. Adding security to make the design secure is sort of a key response to that. And this has led to essentially two kind of parallel efforts, but they're related, which is one, governments creating regulation requiring security in designs. The other is industry defining standards saying this is the level of security as an industry we need within those designs. And those two are very related, but these standards and regulations, we're starting to see them come in many of these industries, and we're going to see more and more of those coming. There'll be industry-specific ones. In automotive, there's UN-ESSA R155, R156. This is binding regulation. You have to meet certain cybersecurity requirements, or you can't sell vehicles within Europe. Related to that is the ISO SAE 21434 standard, which specifies essentially you might call it a de facto standard saying how to implement the requirements of a cybersecurity management system that are in R155. You can similarly see different areas in military having requirements, consumer, industrial, and then you have and medical, which is very recently, in fact, it was just this month that the FDA has revised their criteria for getting devices approved, requiring security to be a part of that, a part of the submission process for approval, starting in just October of later this year. So just a few months away, having those requirements to be in place. Many of these in the US in particular are being driven by the 2020 IoT Cybersecurity Act, mandating needs for security in these systems. In particular, you had NIST 8259, which we'll talk a little bit more specifically, which starts to outline what does that specifically mean in terms of the requirement. So with these kind of contexts and standards and regulations, we'd love to kind of get your insight as part of the webinar, make it a little bit interactive here. You should see a poll come up very shortly where we'd love to know what's driving your need for security. Is that coming from customer requests or needs? Is it coming from an identified need that security is critical to be important? Is it driven by regulatory compliance? Is this a proactive product requirement that you've internally identified? Or perhaps it's another requirement. So if you can respond to that quickly, we'll leave it open for a little bit of time and take a look at the results. Okay, so we see a little bit of everything here. I love the fact that identifying the need for security before it becomes a reactive response to an attack. Being proactive is, I think, a great solution to that. So we're seeing different requirements here. No one clear indicator, but obviously all of these are important: consumer needs, competitiveness, compliance, and being proactive about adding security. So what kind of security should you add? There's a lot of things you can do in security. The security is often should be tailored to an individual product or device that's being developed. This could be driven, for example, by doing a threat analysis and risk assessment, sometimes called a TARA. That would help identify what your threat and risks are, and the security you add is there to mitigate the risks that you've identified as part of that process. But you can also look at, for many IoT systems, you can look at some of the what you might call kind of basic guidelines for IoT security that are probably going to be relevant to the vast majority of those IoT designs. And that is actually where the NIST standard 8259A, which is essentially an IoT device cybersecurity core baseline. This is your roadmap for IoT security. If you don't, without needing to go to do a threat and risk assessment, it's kind of saying these are just the common ones that we'd already know about. So here are the things that you should be considering for your IoT security. NIST identifies 6 of these things. This comes from secure boot, data protection. That is, if you have confidential information, or if you have personal identifiable information, PPI, you want to be able to protect that on the device. So how do you keep that private? You have interfaces that you need to secure. If you have a vulnerability that's discovered in your design and you need to make an update to your software to patch it, you need a capability to do software updates, and that update process should also be secure. You want to be able to securely identify your devices. If your devices are communicating with the internet, you want to make sure that the device that's talking to your cloud infrastructure is actually your device. And how do you securely identify and verify that's the device? Additionally, NIST has what they call cybersecurity state awareness. This is generally a way to understand the current state of the security of your device. Is there an actual compromise? Is there a known vulnerability that we need to patch? How do I actually know the state of each of those devices, what firmware it's on, what's happening, are there anomalies in the execution? So those kind of 6 things roughly translate into what I would call 8 features that you would need to implement. And we'll be talking about several of those today in terms of how to implement them. The first 2 here are related: the secure boot and the extension of the root of trust. So the secure boot is that process. I boot up on power up. How do I boot my system, do it securely so I know it's executing the firmware we designed and programmed into the device? In order to facilitate that secure boot, you typically need a root of trust, saying this is where I start my level of trust, and from there, I can extend that root of trust to verify my bootloader, my firmware, my kernel, my data. Everything beyond that is trusted from there because I have a trusted starting point. Encryption for data is when obviously you have different use cases for encryption. You could encrypt your data, which means it could be your firmware, your code as being part of that data, or it could be the data that you're storing. If you have a medical device, that medical device stores data relevant to the patient. You have to keep that information protected. Runtime security would be the capability to detect if your device is under an attack. Someone's trying to do an intrusion in there. So it could be something like an intrusion detection system, an IDS. If you find vulnerabilities, you find someone's attacking your system, now you need to do your secure over-the-air updates. As part of the update process, you have 2 things you want to actually authenticate. And then we call this mutual identification. You want to make sure that your IoT device, when it's requesting the software update, it's actually your device requesting the update and not someone trying to download your firmware from your update servers. So you want to authenticate in that direction. You also want to authenticate from the IoT device. Is the server I'm talking to actually a valid server that I should be talking to, and not an attacker trying to get a malicious firmware update downloaded? Secure communications. We need authentication encryption to keep things secure. And then we have the debug and IO interfaces. If you have devices where those interfaces may be accessible, like your JTAG interface, you want to be able to secure those so an advanced hacker can't just hook up a JTAG programmer and pull your firmware right off of the device. So those 8 cybersecurity features that we would want to consider for your kind of a baseline for IoT security. So I'd like to spend a little bit of time talking about an example that we're going to be using throughout this talk. Today we'll be looking at, in particular, NXP devices as an example. The i.MX 8M Mini is the one that we'll be using here, particularly looking at embedded Linux. And using that as an example to showcase, well, what does it mean to implement secure boot? What are some of the technical details from that? And then how can we automate that process? In both of those cases, what you end up with is a chain of trust. And that chain of trust starts with your hardware root of trust. And in this case, typically that hardware root of trust is an immutable piece of software. This could be built into the ROM on the device that cannot be changed. And that's your trusted starting point. Your system will boot up, execute the code in that ROM, and from there, that ROM will then authenticate. Okay, before I execute the bootloader, let me verify the bootloader is actually the bootloader that was flashed onto this device. So from the root of trust, we'll authenticate the bootloader. If it was encrypted to prevent, to either protect the IP of the firmware or to prevent reverse engineering, it would also decrypt the bootloader, authenticate it, and then execute the bootloader once you verify it is in fact the trusted bootloader. Your bootloader would then, in a Linux example, it would authenticate your kernel, verify that this is actually the Linux kernel implementation you flashed onto your device. It's a signed kernel, so your authentication, make sure it's correct. Once your kernel is correct, you're going to start executing the kernel. From there, the kernel is going to verify the integrity and authenticity of the file system. That includes the read-only portion of your file system where your applications and services may be deployed, along with the read-write portion of your file system where you would store your data that the device would utilize. You can also encrypt your file system if you're trying to protect the IP or the PII, as well as preventing reverse engineering of people getting application code out of the file system itself. At this point here, you can leverage in Linux a secure over-the-air update process and capability. One example of that is Mender.io. This would support authenticating your downloading updates from secure provisioning. It would enable secure communication. That allows you to update the images in the applications within your file system with updates you get from a secure over-the-air update. And that would start by you running a service that runs on Linux that's been authenticated as part of this chain of trust as well. That chain of trust, each of these components is part of that secure boot process. And there's a lot that goes into this. We can already see that there's, how do I use a hardware root of trust? What do I program in there? How do I get that done? Okay, I have signing, so I'm doing authentication. I have encryption that I need to worry about. I'm applying that to at least 3 different aspects of my system, the bootloader, the kernel, and the file system. So each of these, you can see there's some complexity that goes into that. The starting point, of course, is the hardware itself. Unfortunately, though, most processor manufacturers, they provide built-in capabilities in the hardware itself to facilitate not only the secure boot and the hardware root of trust, but also to facilitate some of the other aspects necessary to support that chain of trust. So generally, you can think of these hardware security features as belonging to a few different general areas. One would be secure boot. That could be the ROM-based software that we talked about already. There are different hardware root of trust capabilities that can be available, but that's the starting point that you have. For the cryptographic functions, you would typically have accelerators inside the processor that will accelerate those common cryptographic algorithms that you utilize. In addition to that, to support your cryptography, you often need random number generation to provide the entropy that's necessary there. The secure storage would be looking at, well, how do I store the keys that I'm going to utilize as part of this process, and what are the access controls around that? You also have device identification. So if you need to securely provision a new device, you want to be able to uniquely identify that device. And in many cases, that device identification is built in either during manufacturing or through a capability such as a puff-based identification that will be unique to every device. You have security monitoring. This is if you can detect anomalies of where your keys are stored in that secure storage. If you detect anomalies in that, your chip can actually clear out all the keys that were already stored there, which would then prevent someone from getting access to that. So it's sort of a protection mechanism around the keys within the secure storage. And then, of course, capabilities for processor and I/O locking to be able to, these are your external interfaces. How do I actually make sure my secure boot is enforced, and if it fails the authentication, it won't boot up the system from there. As well as locking down actual interfaces of the device. So these are the general categories. To look at this more specifically, the specific implementation of this will vary from manufacturer to manufacturer, but there will be a lot of similarities, in particular around the algorithms that are utilized. What I'd like to showcase here is an example of a few different NXP processor devices and the differences you might see in what's supported at the hardware level. And what you'll notice here, though, is with the i.MX series from NXP, whether it's the RT 1160, 1170 family, or the i.MX 6 or the i.MX 8M Mini, you'll see a lot of similarities amongst this family here. So, for example, they all start with a boot ROM. That's your hardware root of trust. In particular, they use a component called the HAB, which is a high assurance boot capability. That's the starting point for the execution. That will start the authentication and decryption of the bootloader kernel application from there. They all have a unique device key that's pre-programmed into the device during the manufacturing. That's called OTPMK, the one-time programmable master key that's done during manufacturing itself. They all have cryptographic accelerators, both for authentication algorithms and encryption algorithms. This is where you start to see some differences. Depending on the processor, you might have more flexibility of what's available in terms of the algorithms that are possible, and you may have more flexibility available in terms of the key sizes that are supported within the processor. So if you notice on the RT, you have fewer built-in size options available for the RSA authentication algorithm, and fewer key sizes supported for AES. But on the alternative side of that in the RT, whereas the i.MX 6 and 8 would typically, they have the accelerators when you're booting up an encrypted image, you would decrypt the image, load it into RAM, and then execute out of RAM. The RT supports the capability to do an execute in place, XIP, and have encryption applied during that execute in place. You're executing directly out of your flash, but on an encrypted image, so you're not actually decrypting. You're decrypting it internally to the processor. And then you'll see all of these support some variety of random number generators. They have a few differences in terms of the availability of secure storage, and they all have a one-time programmable fuse-based locking capabilities for how do you control the source for your boot, your IO logging, JTAG security, etc. So there's still a lot of these details here. There's several different cryptographic algorithms that are supported. There's different key sizes. There's questions about how do we use how do we use the OTP-MK, and this is where you start to get into the complexity of implementing security. And what do we mean by the complexity of security? So if we consider that chain of trust, we have to think about how do I use a root of trust? How do I authenticate and encrypt my bootloader? How do I do the same for the kernel? How do I do the same for the operating system? How do I handle processor logging? How do I handle secure over-the-air updates? Added to that, we have decisions around where the algorithms are going to be used. How do I do those algorithms? How do I program into my devices? So I won't go over all of these questions, but to get this, to understand kind of the complexity of the security that's involved, we look at the bootloader authentication. You're starting from, I need to add security. There's going to be a series of questions about details you need to figure out. So the first is what algorithm to use. There's a few common options. RSA is very common, a good algorithm. So you might identify RSA. It's an asymmetric algorithm that you can use for authentication. Well, now I need to identify, okay, I know the algorithm, but what key size do I use? There's a trade-off in the key size. The bigger the key, the longer the authentication takes as part of the boot process. So if you're time sensitive to your boot process, you might consider using a smaller key. The trade-off is a smaller key means that as computing capabilities become more capable, there's a potential those keys could be compromised in the future due to quantum computing. So there's a trade-off there, and you might have to decide how long is this going to be in service. Once you've identified your algorithm and your key, now you get into more of the implementation details. Okay, how do I generate the key? What tool should I use for that? I have the key. How do I actually sign my bootloader image using that key? How do I then, now that I have a signed bootloader, how do I tell my root of trust how to use my key to authenticate my bootloader? So I don't actually program that into my device. That's where you start getting into questions about the layout of the firmware and the various offsets different things need to be at so you can instruct the hardware of how to do that boot process. Do I have to program some fuses in order to enable the secure boot? Once I've done this for the bootloader, I know I want to do authentication for the kernel already. So you start to get into questions of, well, can I reuse the key or do I need a separate key? Do I need a per product key? So can I use one authentication key for all the devices of a particular product that we're going to ship? Or does that key need to be done on a per device basis? And then of course, well, now that I have all these keys, how do I securely store them? So there's a lot of details that go into this process. And one of the challenges is that it's not only important to understand all the things you need to implement, but also make sure that those implementations are done correctly and in a secure manner. It really is as simple as if you make one mistake in one of these kind of key critical aspects, that's all an attacker may need to be able to get access and compromise a device. An example of this is a few months back, there was a vulnerability demonstrated in a Hyundai infotainment system. And they actually had security implemented. They had authenticated firmware. They were using encryption to protect their firmware as well. So they had all of that implemented. They locked down the system as well. The challenge that they faced is that what ended up happening is they reused a set of example keys that were available in an online tutorial. So rather than generate their own keys, they reused that example. So in getting access to the firmware, they were the hacker was able to identify, okay, I know what the public key is because the public key will be part of your firmware image. That public key matched a public key that was, you could just Google for that public key and find the tutorial for that. And because it's a tutorial, the private key that corresponds to the public key is also available in the tutorial. So now from that public key, you could sign a new firmware image and flash it onto that device. So that's an example of making sure you're generating your key securely and you're also storing your key securely. So what I'd like to do is provide a little bit more detail of how does this all work. So again, we're going to use the NXP, this i.MX 8M Mini as an example of how that works. So we'll look at a few of the details here. So we'll start at the bootloader and doing the bootloader signing. So there's really two key steps to the bootloader process. The first is the key generation. So you have to generate a set of RSA keys. Each key that gets generated, there's a public and a private pair. The private key is used for signing your image, and the public key is then going to be added to your firmware image and programmed into the device. So there'll be two aspects that this is done in order to do that security. So if I generate for my keys, I'm going to take that key, and there'll be two things I need to sign in my bootloader image. There's the image itself, that's your raw bootloader code, and there's also on NXP what's called a command sequence file. The command sequence file is essentially a recipe that tells the HAB, here's basically the partitions of memory where my bootloader is located. Here's where I've stored my key. I'm using this particular authentication algorithm. The key is of this size. Please authenticate the image for me before you proceed on with the process. So it's basically like a recipe telling the HAB how to implement the secure boot. What are the checks it needs to perform along the way? So with the private keys that you would generate from there, you would sign your bootloader image and sign your command sequence file. That gives you now your binary, basically your signature that you're going to add into your image. You'll combine that with the image itself. And now you have a signed bootloader image. And using a tool such as UUU, this is a tool from NXP that allows you to basically program very efficiently over an SDP interface. You can flash that image into the flash of your device, and now you have your signed image in your device. In addition to that, what you also need to do is generate a hash of the key that was utilized. So that key, we'll call it, there'll be what's called a super root key. This super root key is that first key that you want to authenticate is the actual key. So you would generate a hash of that key. So that's now what's called your SRK hash. And you would program that into the one-time programmable fuses. So the hash of your key is now in the fuses. So as part of that high assurance boot, what the boot process will do is it'll look at the public key that you've appended into your firmware image. You will compute a hash of that key. The bootloader will then compare the hash of that key with the hash that was programmed into your one-time programmable fuses. If those match, it will then use that public key to authenticate your firmware image before it boots the process. If the key doesn't match, then it would say, oh, these don't match, I'm not going to boot my device. So it's part of that secure boot process. So there is this hash programmed into the fuses for that secure boot. So in doing this, you'll notice here that to facilitate all of this process, there's also 4 different tools that you need to utilize. These are all NXP tools: UUU, a code signing tool, an SRK table tool, and a PKI tree tool. Those are tools from NXP that you can utilize that they're provided. So there's good support for that to be able to do that. But obviously there's learning all the details of how these come together, part of that process. So hopefully this explains some of how all of these tools go together for that. But it gets a little bit more complex now once we start talking about encryption as well. Because now not only do I have the authentication to worry about, I have to worry about the encryption. And so now the offsets become a little more important because there are certain portions that you can encrypt in your image and certain portions that you can't encrypt. So I won't go over all of the details here, but I wanted to highlight one aspect which is fairly important for NXP, which is what's called a DEC blob. So a DEC is short for, generally means a disk encryption key. So that's the key that we're actually going to encrypt our image with. It's a symmetric key. So I don't want to I need the same key is used for encrypting as decrypting. So I need to know that key at runtime in order to decrypt my image in order to boot it. But I don't want to just store that key in my flash, because then anyone who can get access to the flash, my key is there in plain text for them to see. So that key can be secured with what's called a blob. Basically, it's an encrypted version of that key. So what you could do with that DEC key is you can actually send the DEC key to the i.MX, to what's called the CAM, the Cryptographic Accelerator and Assurance Module, and you can ask it to encrypt it as a blob. You'll then get back a blob from the device, and you can, for that blob, you now apply that blob to your firmware image, so now it's only in your flash in an encrypted form as part of that process. We've developed a modified version of UUU to facilitate automating that process, because in order to create that blob, you do need to communicate with the device you're actually programming. So we now have the keys we need for authentication. We've done our signing, we've generated our DEC blob, we've done the encryption, I have my image, it's programmed into my device. And now I need to do some additional steps to actually lock down and enable the secure boot. If you just do that programming, if the secure boot process fails in what we would call an open board, an unsecured state, it'll still boot. So you can debug the process and make sure you've done stuff right. But when you go to production, there's a set of fuses you want to actually program to enable the secure boot. So you want to be able to have, for example, there's two sets of fuses. One is critical to closing the board to only allow authenticated images. And that would be a fuse called setConfig. You have the SRK hash we talked about. You have to program that. And then you have SRK lock, which is sort of a safety mechanism to make sure you don't accidentally program another hash over your SRK hash. You can lock it down and say no more programming allowed. You have a separate set of fuses that are basically to lock down the board, to be able to say, okay, I want to disable the SDP protocol so somebody can't read my firmware out. I want to enable a secure JTAG implementation that requires a password in order to enable JTAG. So there's a set of these fuses you want to program. There's also fuses that you want to program to configure the boot state. If you don't want to allow your GPIO pins to change your boot mode configuration, you can force internal boot and then configure how the system will boot. And then on a few older versions of the i.MX, if your hardware has an older version from that, there is a test mode that was enabled coming out of manufacturing. So this fuse called DIRBT disable. If you're on an older version of the hardware, you would want to program that fuse, which disables this test mode on the system as well. So, okay, we've programmed setConfig, we've programmed the SRK hash, we've programmed the SRK lock, and what actually happens now is we're not actually done because of how the DEC blob is generated. When we configure the board into a secure state, there's now a difference in how the CAM generates and encrypts that DEC blob. So on an open board, that DEC blob uses a test key. And so this is great for testing. You want to make sure that the process works. You're able to generate the DEC blob. You can take a known encryption key, run it through this test key, which is known, and then you can check your blob to make sure it was accurate. So you can verify that. Once you close the board, in other words, once you program that setConfig fuse to enforce only booting authenticated images, you'll now utilize that one-time programmable key in order to encrypt the DEC to produce the DEC blob. So your flashing sequence for an authenticated and encrypted firmware image, there's sort of a procedure that you need to follow for that. So you have to flash first a signed bootloader. You can then close the board by programming those one-time programmable fuses. Now the board will reboot into a secure state, at which point you can use the CAM to generate your DEC blob that will be encrypted by your OTP-MK. And then you can flash over your encrypted image with that DEC blob into your firmware. And now if you reboot the device, it will decrypt your image and authenticate it as part of that boot process using the HAB and the CAMP on the i.MX 8 So there's a lot of this complexity. There's these procedures you follow, doing them in the right order, generating all of this. And so this is where, given all of the complexity we've talked about in these technical details, it is possible to figure it all out and implement it all. But again, this is where automation can really help facilitate the process of making that much more simple if you know what you need to be able to do. And so at BGN Networks, we have a tool called BGN-SAT, which is our security automation tool. It's a first of its kind automation tool, really. And the goal of that is to accelerate the implementation of your baseline security requirements for your system. So the goal here is to be able to not take months of engineering time to figure out all of these details and make sure they're all implemented correctly, but be able to do that in a matter of days, really. And by doing that efficiently and automating that process, hopefully that means that you don't have to trade off adding security to your design because that might delay your product schedule. So the goal is to be able to implement security without really significantly impacting the development time. So the key features of this, and we'll show a demo of this today, the key features are being able to do a step-by-step security needs assessment, key generation, signing of your code, encrypting your code, locking your processor, downloading it to the flash, and handling those sequences of, hey, I need to generate the DEC blob. How do I do that? So currently our tool supports, right now we have support for, we've been talking about NXP, so in particular we support the i.MX, the RT, the i.MX 6, the i.MX 8, both with embedded Linux as well as with Zephyr as another alternative. So before I jump to showing a demo of the tool, I just wanted to talk a little bit about what does that software stack utilize. So we do have for Yocto, we have a meta layer that we provide. We call that BGN-ESSA. And this is really a simple layer that you can build into your Yocto implementation that will enable the Linux security features you need for authentication and encryption of your root file system, making sure you have the drivers necessary for utilizing the cryptographic accelerators, doing the basic configuration to set up your Linux build in such a way you can do this authentication and encryption using the hardware capabilities, the root of trust from that. So on the right-hand side here, just showing that stack, you have your, at the bottom, kind of in the gray area, those are really the baseline features of your processor that you just need to make sure you have the right drivers available for it. For U-boot and Linux kernel, we're using RSA for authentication and AES for encryption. In your root file system, it's configuring DM integrity and DM crypt. This is for the integrity and encryption necessary at the file system level. And then as well for secure over-the-air updates, Mender.io, providing a basic integration of that. I'll just very briefly show Zephyr. You'll see some differences in Zephyr because the architecture is slightly different. In this case, for Zephyr, we're using execute in place, so it uses what's called OTF-AD, on-the-fly AES decryption. So that's a capability available in the RT platform that we can utilize as part of Zephyr. It's using a different bootloader. In this case, it's MCU boot instead of U-boot. And Zephyr, if we look at the over-the-air update level, Zephyr supports already, they have built-in support for encrypted firmware updates, as well as downgrade prevention, so we can utilize those. That's where you start to see some of these difference between each of the operating systems that you have, but for the most part, it's still following a similar process. So I think we have time for really quickly here to pop up another poll before we switch over and do a demo of BGN-SAT. Really, since we've been talking a lot about the NXP i.MX, series, so we're curious which of these processors you might be using in your design, or perhaps you're using an alternative one here. Okay, so we see, I think we have a few responses. Not everybody responded to the poll, but we have many of you are not using any of these, which is fine. Most of the secure boot process, each processor manufacturer does have different capabilities to support secure boot, but the basic requirements are the same in terms of automating, adding authentication, encryption at each of the stages of the boot. The differences are some of the basically the lower level tools, and so those are obviously some things that will have some differences here. And what we seek to do with our security automation tool is to abstract that away from the engineers in the manufacturing and automate that process and abstract that to the high level of defining what are the needs of your system, and then we can automate the rest and leverage whatever capabilities are in each of those processors. So in order to use BGN-SAT, we talked about the meta-ESSA layer. I just want to point, if you're interested in looking at this for the Yocto build, it is available. It is open source on our GitHub page. It's github.com BGN-Networks meta-ESSA. The goal here is with Yocto builds, it's a straightforward meta layer that you can download. So it really is as simple as download the manifest for that into your Yocto build. In your repo init, reference the meta-ESSA layer, and then when you're setting up your build environment, we have a setup script that you can source as part of that build to configure that process. And then when you do your bit bake, you end up, when you do bit bake for your core image base, you get 3 outputs from that. You have your bootloader, uboot, which the file here for a Kirkstone build, the default file will be called i.MX boot tagged. You have your kernel, which is called z-image, and then you have your core root file system image for your image base here, which would be the rootfs.wic file. Those are inputs to BGN-SAT. So those are the files that would be input here. And what BGN-SAT will do is generate all the keys necessary to do the signing and encryption of your images. It'll sign and do the encryption, flash it to your device, and program that. So what I wanted to highlight in this slide is really that what we want to make sure we're doing is decoupling the firmware build process from the device programming process. So when you're going to manufacturing, you don't want a build system part of your manufacturing process, because you have to communicate with each board to generate that DEC blob as an example. You need to have some of the signing process and the flashing done as part of that automation. So not only do we support the engineering development where you have to define what security is needed, but then enable during manufacturing a straightforward handoff of here's my unsecured firmware, here's the security profile that we have, and then when you go to the manufacturing process, you can fully automate the device provisioning, including the key generation that's necessary to do on a per device basis. This is just, I won't spend any time on this, but this is really just a quick overview of all the keys that are generated. There's about 17 different keys that are needed, or hashes, cryptographic material that are generated in this process. But with that, I will stop now and switch over to a demo of our tool. Let me stop my share briefly and reshare. BGN-SAT. So we're looking at our security automation tool here, and I wanted to just kind of showcase what we're able to do. So the first thing you would do is define what we would call a security profile. So I'm going to define a new profile. And then as part of that profile, this will walk through what we call a guided security assessment. So what this is going to do is walk through each stage of that bootloader process. These stages are specific to the OS that you're using. So if you're using embedded Linux, you would have your bootloader kernel, your OS, and then your fuses. If you're doing a Zephyr build, for example, this process will actually change, and we would be doing just a bootloader and application because the application and kernel are combined in the Zephyr implementation. In this case, we're doing an i.MX 8M Mini and embedded Linux. I'm going to choose an output directory. This is where all of the artifacts will be stored. Your keys that are generated, your signed firmware images, if you need access to those will be stored in an access directory. And then we can get to, okay, how do I then identify what I need for my bootloader? So the first is the inputs to my system. So I would need to choose my bootloader image. And now I want to decide, okay, do we need to authenticate? So we want secure boot, so we definitely want authentication. We do have to choose the size BitLoader. And in many cases, I would recommend you use at least 2048. If you're going to have your system in production for a long time, we would recommend 4096, particularly if you might have it there for 20-year kind of production cycle, because quantum computers likely are going to be able to crack 4090, some of those smaller key sizes, I should say, within 20 years. If you're unsure of that, we do have help built in. So we try to provide some guidance here. So if I click on the key size itself, we'll highlight some recommendations, for example, that come from the National Security Agency, and just a little bit of detail about why you should consider this, particularly around quantum computers. Similarly, you can do the same thing for encryption. So here I'm going to go ahead and encrypt the bootloader. I'm going to use 256-bit keys for that. And then we can now choose where are we going to flash that. So there's different architectures where you can store your bootloader and kernel. In this case, I'm going to put everything into eMMC. And for the flashing tool, we'll just use NXP's built-in SDP protocol. I would do it similarly for the kernel. So I would grab my kernel image here. Let's authenticate it as well. Similarly, 4096-bit key, and we'll put the kernel in eMMC, and again, we'll use SDP for flashing. And then at my OS level, I can simply choose my root file system image here, and then choose whether or not we want to encrypt the firmware image. This brings us to the fuses. So as we talked about before, minimally the fuses you would want to program for secure boot is the sec configuration. So we can enable that, and the SRK, so that will do the SRK hash and the lock. Both of these are necessary for that. If we have an older production on i.MX 8, we'd want to program the DRBT dis flag as well. And then the rest of these are going to be related to how much do I want to lock down the other interfaces. So for example, secure JTAG, instead of being a close, I could secure that with a password, and then I could provide the password that will secure the JTAG interface with. And so at this point, this would be defining my whole security profile, and I can save that profile. If I go back to the home here, you'll see that profile was enabled there. I can edit the profile if I need to make changes. And where it took us before is directly to the device programming phase. So at this point now I can enter in my board ID, and I can specify, in this case, I think it's COM4, and then the SDP board that's being utilized. If I click Program Board, this will then facilitate that whole automation process here. It takes about 5 minutes to do that. This is also my development board, so I don't want to actually program the fuses. And so I won't show the rest of that full programming process, but it does automate that whole key generation, device programming, signing, encryption, fuse programming, handling the appropriate reboot sequences that are needed along the way to do your device locking. So let me switch over back to the slides, and we can kind of wrap up. I want to make sure we have some time to answer questions that may have come up. We're fairly confident in, if you're utilizing one of the processors and operating system combinations that we already support, the automation that we provide with BGN-SAT, we're very confident that you would be able to secure your design in the matter of a couple weeks. And we're willing to say if you're using our tool and you're not able to secure it within that couple weeks for the supported processors and operating systems that we already have, we will help secure it for you. And so I want to make sure that you're all aware of that. We have evaluations of the tool available as well. And again, I think we have a little bit of time here, about a few minutes, to answer some questions that may have come up. Gary, have you been monitoring the questions?
I have. I've answered a number of them throughout, but we've got a couple that are queued up for the end here. So the first question is, how does the BGN tool generate the keys? And the suggestion is mainly entropy. And is there an option to export these keys to an HSM?
Both excellent questions. The key generation we leverage for the key generations, we're currently utilizing OpenSSL. Entropy is definitely critical for that key generation. OpenSSL and we are not recreating that key generation process, but rather leveraging known capabilities, known software. And so for our case, we're using OpenSSL. If there's an alternative library that you would want to utilize, such as WolfSSL, that's certainly an option that can be added to support that. I think OpenSSL, the latest version, is also on the pathway to FIPS certification, which I know is very critical for many applications, in particular where they'll be used by the U.S. government that's requiring FIPS certification for the cryptographic algorithms that are being utilized. In terms of how to store those keys, there's several different ways. Can an HSM be used? Absolutely. You can also utilize, there's different ways you can do that. There's cloud-based infrastructure that's possible as well, that can be integrated to the key management system that if you already have that set up. So that's something that we can tailor to your needs of how you're storing your keys if you already have a PKI infrastructure in place. Or you can also, if you, at the sort of simplified model, but maybe a little less secure, you can also utilize a secure PC and store those cryptographic artifacts on the secure PC. That's obviously a little bit less secure than utilizing an HSM or a cloud-based PKI infrastructure or a TPM. So hopefully that answered your question.
Sorry. Yeah. In the interest of time, since we're at 2 o'clock, maybe just one last question that was asked is, do you offer training for companies on embedded security?
Yes, we absolutely do. We have a workshop. We've given this a few times. The workshop is meant to be no requirements necessary for cybersecurity, but explain the basics of that. Our default configuration for the workshop is a 2-day workshop that can be tailored down to a 1-day workshop, or can actually even be more in depth and offer further ones. So we do offer trainings and workshops. Again, we would tailor those to your particular needs. If you're in automotive, for example, we could cover ISO SAE 21434 requirements. If you're in more in the industrial field, we can cover some of the relevant standards there as part of that training. So the short answer is yes, we do, and we can tailor it to your particular needs.
All right, great. I think that's all that we have time for today. If there are any additional questions, please don't hesitate to reach out to us and we'll get back to you as soon as possible.
Thank you very much, everybody. Appreciate you joining us today.